In the previous lecture, we saw that negative numbers in a computer are represented using 2's complement, because that's a really simple way to add or subtract numbers. If you want to convert a positive number into a negative number, just take 2's complement. If you want to convert a negative into positive, just take 2's complement again. And we in the last lecture we did not discuss this example. If you want to subtract 7 from 12, so let's try to do this example. And we saw that we cannot represent 12 in a 4-bit number, because the 4-bit number in a signed format has the maximum range going from -8 to +7. What we can do is we can use a 5-bit number, or we can use an 8-bit number as well. So if we want to discuss, if you want to see how those numbers actually work, so for 12 what we can do is, let's start with a simple 5-bit example, even though 5-bit is really not that standard. But let's say if we have hypothetical system has 5 bits, so this bit is signed bit, and this 1 2 4 8 and this thing would represent -16. So if I need to represent +12, so what I'm going to do is I'm going to do the signed bit as 0, and this thing would be 1, and 8 plus 4 is 12, and all of this thing would be 0. And if I have 7, positive 7 is actually, if I just turn on these bits like 0 0 1 1 1, I have positive 7. If I need to convert it into -7, what I need to do is take the invert all bits, so I get 1 1 0 0 0, and then add 1 to this number, so I get 1 1 0 0 1. So this thing is equal to -7 in binary format. So if I want to do is 12 minus 7, what I can do is equals to 12 plus -7. So I'm going to write 12, the binary code for 12, if I'm talking about a 5-bit number, 0 1 1 0 0, and the negative number would be 1 1 0 0 1. Just add them together, I get 1. 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 0, 1. 1 plus 1, if you remember, 1 plus 1 is 2. In binary, that is equally this thing, 1 0, and I get 1 plus 1 is 0, and I get 1 carry, and you just discard this thing because we only have 5 bits to work with. We started with 5 bits, and we are just assuming that we only have 5 bits to work with. So what I get here is I get 0 0 1 0 1. So 1 0 0 0 1 0 1 would be 1 2 4 8 -16. So 4 plus 1 equals to 5, and 12 minus 7 is 5, and that's how we do the arithmetic using 2's complement, because we only do addition for subtraction as well, because we represent negative numbers with their 2's complement part. And let's take another example. Let's say if I want to do 8 minus 14, I want to do 8 minus 14. So what I can do is I need to represent 8, and once again I cannot represent this thing in 4 bits because max 8 minus 14. If I have 5 bits, 1 2 4 8 1 2 4 8 minus 16, so the maximum number is -16 in negative, so I can easily represent this thing, and I can also have +8 over here, so that's, we are okay with that. The same rule apply with 8 bits. I mean 8 bit would go all the way to -250, -128, and so on and so forth. So let's try doing it with 8 bits if anybody wants to. I mean, it's really not that difficult. I can do it in 5 bits as well, so let's do it in 8 bits. So I'm going to do 8 minus 14. I'm going to do let's pick another pen. I'm going to do 8 minus 14 in, if we had an 8-bit signed format, 8-bit signed format. So 8 is, we have 1 2 3 4 5 6 7 8, 1 2 4 8 16 32 64 and -128. So 8 is just put 1 over here and all zeros over here. So this is equals to +8, because the sign bit is actually 0 over here. Now for 14, what I need to do is I need to convert, and first I need to write what is actually +14. So I have the placeholders for the bits. So 1 2 4 8 16 32 64 and 128 in minus. So if I write 14 over here, so I cannot turn on 16 because the resultant number would be more than 14 obviously. If I turn on 8, I just need to turn on 6 more, so I turn on 4. 8 plus 4 is 12, plus 2 is 14. So and I just sorry, not here, and I just do 0 over here. So to convert plus 14 into minus 14, what I need to do is invert all bits, and then what I need to do is we will first invert all bits. So I get 1 1 1 1 0 0 0 1. 0 becomes 1, 1 becomes 0, and this all zeros become 1. Then I add 1. So what I get here is 1 plus 1 is 0, 1 carry, 1 0 0 1 1 1 1, and this thing is equals to minus 14. So what I need to do is, originally what I need to do was 8 minus 14. So I'm going to add, this thing is equals to 8 plus minus 14. I have the binary code for this, and I have the binary code for this, and I just need to add these two binary numbers together to see how the computer actually adds the numbers to actually subtract the numbers. So what is 8? 8 is I need to write it somewhere, so let's write it over here in some other pen. If we have, what pen? Red. Okay, so what we need to do is 0 0 0 0 1 0 0 0, that is 8, and I'm going to add this number. I'm going to add this number. I'm going to write 1 1 1 1 and 0 0 1 0. Just add this number and see what we get. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1, and 0 1 0 1, we get all ones over here, so we get this number. And let's convert this thing into decimal format and see what we get over here. So we have 1 1 1 1 1 0 1 0. I'm going to write the placeholders, I mean what these bits actually represent. So this bit represents 1 2 4 8 16 32 64, and the last bit represents minus 128. So whatever bits are on, I'm going to add them together. So I will get minus 128 plus 64 plus 32 plus 16 plus 8. I'm not going to add this bit, I'm going to add this one, plus 2. So what do I get over here? Let's use the calculator to see. Okay, calculator. We have minus 128, so plus 64 plus 32 plus 16 plus 8 plus 2. So I get this thing equals to minus 6. So I think 8 minus what the original thing was, 8 minus 14 equals to minus 6, and that's how we get a negative number represented over here in 2's complement format. So coming to our program, and let's see how it works. Let's open some example, or let's write a new example. So in this example, I'm just going to output some numbers and see what those numbers actually look like if we are talking some signed numbers and in hexadecimal format or in binary form. I think binary format is not possible unless you write some function to display. I mean, internally computer actually processes binary numbers, but it displays them in hexadecimal for easier reading. You can write some function to represent those binary numbers. So what I meant to say was displaying binary numbers without writing some elaborate function in C++ is not built in there. You need to write some functions. I'm going to display using hexadecimal. We mean exactly the same thing. So first thing, I need to write the basic include preprocessor directive, which is IO stream, and I'm going to use standard namespace and integer main void, and I'm going to write return 0, and I'm just going to see out some numbers. So see out and just a number, for example 12, and see what we get. Obviously we have 12 over here, so let's run this thing. F11, it says save this thing, so I'm going to save this thing as temp is already there, temp1. this is 12 over here. I think you can use the properties over here to change the font as well as the layout and colors as well to make it easier to read, and it says 12 over here, no problem at all. What I need to do is I need to display this 12 in hexadecimal, and actually for binary you need to make or write your own function. It is also available probably on GitHub or something like that. You can look it up on the internet. So what I'm going to do is I'm going to go to this website c++.com/reference/ios/hex. So this thing is base field format flag, whatever number. Let me give you an example how this thing actually works. So if this thing is actually a number, let's say this, in this example this thing is actually 70, and if I set the base field flag, if I do not set the base field flag, that will display a decimal format by default, because this thing, whenever this thing is started, this is set to decimal on initialization. If I set it to hex, it will display this thing in hex. So let's see what that 12 in hex is. So what I need to do is I do not need to write std again and again, because I'm also already using the standard namespace. So it's understood that all of these initializers and the variables and the object identifiers belong to the standard namespace, so do not need to write the std again and again. So what I'm going to do is that coming to here, so what I'm going to do is I'm going to write hex. I need to convert this 12 into hex, and then I need to put that in the output using the cout object. So let's recompile this thing and see what we get. It says C over here, and C is A is 10, B is 11, and C is 12, and I think we are okay with that. So let's say if we have a bigger number, let's say we have for example 150, and we recompile it again. So what we get over here is, in hexadecimal format we get 96 in hexadecimal format. Let's say we have a number, for example 255. So what should we get if we have a 255 over here? We are getting FF. So all ones here on all ones here. It is understood to be an integer, and it's actually a 2 byte or maybe 4 byte number. So it's not it's not displaying the non-significant zeros over here. So it is essentially all ones and all ones over here, and it contains zeros right before that. So going to, let's say if we have a number, for example minus 120, or let's do some maths. Okay, so let's have 8 minus 14, and just to put in brackets, so 8 minus 14 is minus 6. So 8 minus 14 is minus 6, and let's see what we get. Let's delete hex here and see what we get over here. It's going to solve 8 minus 14. It's going to display minus 6 as expected in decimal. Now if I put the hex modifier saying that whatever integer is coming in this stream should be displayed in hexadecimal format. So if I run this thing again, I get this thing 1 2 3 4 5 6 7 F's and A. So let's hope this is not some mark sheet. So A and let me count it again: 1 2 3 4 5 6 7 8. Do not worry too much about the case, because the capital or small case are essentially the same thing if you are displaying some numbers. The code of C++ is case sensitive, and the strings whatever you display are obviously case sensitive, but here the numbers are displayed. It really doesn't matter what font or what case they are displayed. This is essentially a number. So we have 1 2 3 4 5 6 7 F's and A. So let's see how it works. Behind the scene, this thing is actually represented by 2's complement. Coming back to this thing is a large example, so coming back to some space, let's write that thing again here. 8 minus 14 is minus 6, and computer is displaying this minus 6 as you can just write capital, no problem. 7 F's and A. I mean, computer was displaying like this, F F F A, something like that. I mean, you can just represent smaller capital letters, no problem at all. So let's convert this thing into binary format. So this A is in hexadecimal. This A is 1 2 3 4 5 6 7 8 9, and A is 10. So 10 is, if you want to display A is equals to 10 in decimal. If you want to display in binary, so we can have in binary, so 1 2 4 8. I mean, take it as unsigned if you want to. I mean, just we are talking about each hexadecimal number can be represented by a 4-bit number, so we can have 1 0 1 0. So this A is 1 0 1 0, and F was 15 in decimal. So 15 is 1 2 4 8, 1 2 4 8. Take all ones, 8 plus 4 plus 2 plus 1. This is 15, and this is A. So we have, I mean, this thing is represented by this thing, and this thing is represented by this thing. I mean, we have a really large number, and sorry, and this thing is like this thing, and this thing is this thing. How many bits do we have? 1 2 4 3 5. Sorry, 1 2 4 1 2 3 4 5 6 7 8. We have 8 groups of 4 bits each, so we have a 32-bit signed number. 32-bit signed number. So what I'm going to do is I'm going to pause this recording, because that will be slightly boring for you if I write all the placeholders here. So I'm going to write this, I'm going to pause this recording, and I'm going to the new page to write the placeholders, or so that, or if you want to really, so all the placeholders, I'm going to convert this thing into a, I mean, whatever the actual thing is representing. This thing is like, this number is actually representing this -6 over here. There is an easier way to do that. If you want to know what this number actually represents, just take the invert all the bits and add 1. You will get +6. That means the original number which we took the 2's complement of was actually -6. So, but for completeness sake, I'm going to pause this recording over here, and I'm going to write all the placeholders here. Okay, coming back to this problem. Actually, I paused the video to write the numbers. I mean, what I did was, because this is a really large 32-bit number, so what I did was I wrote these numbers, and I wrote their placeholders using calculator or Excel sheet if you want to. Whatever bits are activated, just add them together. Whatever bits are not activated, just leave them, because 1 and 4 are not activated, the rest of them are. So what I'm going to do is just add all the placeholders, whatever activated, and these numbers are really small, but you can just use using some calculator. Essentially, each next value is the double of the previous value, and the last value, this value, is actually negative. So -2.1 billion, this is 1 billion, this is 500 something million, and so on and so forth. So if I add these things together in Excel format, or just copy these values to Excel, whatever bits are activated, I'm just adding those numbers together. So if I add these numbers together, so this thing is actually a sum of all these, sorry, it's not on your screen. So going to Excel, if you add these numbers together, whatever bits are activated, the most significant bit is negative, and if you add them together, so you get a -6, which was the original output, where we had this thing as this thing inside the computer represented as the bit pattern which we saw, and this thing is actually representing -6 over here. A really simple way to without doing all this work, what we can do is that if you want to convert this number, because this thing is a very long computation to do, but computers, it's not that difficult to do. Computer just represent this thing as bit patterns. This thing is -6. So what we can do is, if we want to convert this bit pattern into what this thing is actually, for easier doing, so just take the 2's complement, so and add 1. So this thing would become if I take the 2's complement of this thing, then all of these ones would become 0. All of these ones would become here the 4th group and the 5th group and the 6th group and the 7th group of ones become 0, and this thing would become 0 1 0 1. That's the significant part over here. So I mean, and just add 1 to it. So if I add 1 to this, so this thing would become 1. If I add 1 to it, this thing would become 0, and 1 1 0. 1 is carried over here, and all of this thing would be 0. So this thing is 1 2 4 8. So 4 plus 2 is 6. That means the original number is actually -6, because we took the 2's complement. Now we have 6. So that means the original number would have been -6 over here. So instead of doing this very long computation, just to emphasize what the computers are dealing with and why they are so quick in solving the numbers, but instead of doing this computation, we just take the 2's complement to figure out what the original number was. Now if we I mean, that concludes the first topic here, in which we can represent negative numbers using signed integers. So whenever I'm declaring integer a, that is understood to be a signed integer. And if you want to take a look in the next part of this lecture, if you want to take a look at what are the ranges of these numbers are, so I can include I think the file name is C limits. So let's see if we can get, yes it is. So if I press control, my cursor becomes a hand, and this thing can go to whatever is defined in these preprocessor directives. So I'm pressing control, and if I click this C limit header file, this is a forwarding header, and it has the definitions of the limits of these files. So if I go to limits.header file, let me rephrase what I did. If I go to C limits, it will open the code for C limits, and it has the definitions, and define is essentially similar to constant, but they are essentially defined globally. And one more thing is they are quite similar to constants, because for our purposes there are slight subtle differences, but they are now beyond the scope of this lecture. But let's go to the limits.header file. So if I go to limits.header file, it says that what is the maximum minimum limit. So if we have short minimum and short maximum, when talking about the short over here, going to probably see the example. We have short over here, we have integer and long, and unsigned short, unsigned integer, and unsigned long. Unsigned, the minimum number would be 0 obviously, and the maximum number would be let's see, short minimum is, this is signed short minimum. So short minimum goes from -3 to 768 and goes all the way to 3 to 767. That means it's a 16-bit number. So if I'm declaring a short variable, it's a 16-bit number. Had it been an unsigned, so unsigned short maximum is FFF, and U means unsigned. So that means if we have 4 F's written, so that means an unsigned number. A minimum is obviously 0, so no need to write that. So if an unsigned number, so unsigned number is goes from 0 to all F's, and all F's, if you have 4 F's written over here, so let's what we get over here, I think we saw that in the previous lecture. So go to lecture 10, and if we had a 16-bit, let's see what we have, 4 bits, and we have this is 4 bits. If we have an 8-bit number, and we have 16-bit, so it's 16-bit goes from all F's, and it goes to 65535 in decimal format. So obviously we would be dealing with decimal format, so that's why it's taking as unsigned maximum would be 65535. But if you're talking about the signed short integer, it has 16 bits or 2 bytes, because each byte is 8 bits. That means that it will go from -3 to 768 to +3 to 767. And that's why we did in the previous lecture. Where is that? Okay, So what you have an assigned integer, which is actually short as defined in C++, shrt. It goes from -32768 to +32767 because the negative number, because it's also using the sign bit as the magnitude bit as well. So it goes from 16-bit signed would go from, let's write it here. So it will go from 1, and you just write like this. So it is -327632768, and it will go from all the way to 32767, and that's what it is defined over here. So I think you might have noticed that if it's going to define some really large numbers, so it's going to define them using hexadecimals, or let's see, integer minimum, integer maximum. You can see that goes from -2 billion to +2 point something billion. Let's see, it's 21447. I think I made a mistake over here in the previous lecture writing these numbers, unsigned numbers. I think it is 4294. I should have written this 4 over here. Is 42949679295. So it goes from, if we have an unsigned integer, it's a 32-bit number. So it goes from all f's, 8 f's over here, and let's see what we have. We have unsigned integer maximum, and it has 1 2 3 4 5 6 7 8, and u means unsigned over here. So it can only have positive value and 0 to positive value. Positive value is I mean, if you write 4, if you know 4 not 4 8 f's, so this thing is actually equal to 4 point something billion over here. So 4.24294497296, and this is a way of writing really. So 0x means this is, I mean, we are going to discuss how we are going to input the hexadecimal if you want to. 0x is representing that the number coming in is a hexadecimal number if you are trying to input an hexadecimal number over there. So I'm going to demonstrate that in an example whenever probably in the next lecture. Okay, undefined integer minimum, integer maximum, it goes from 21474483647. I think we derived that. Where is that? I think it should have been here. So 32-bit signed, that's what we have here, 21474483648, and we discussed that in the previous lecture. 21474 where is that? 21474483648 and 21474483647, because the positive number has one less than the maximum possible minimum number in magnitude form. Reason is because we are also counting 0 as obviously as a number, so positive numbers would have one less. I think we discussed that in the previous lecture. So it's 21474483647, and that's what we have, 7483647. Unsigned long minimum, unsigned long maximum has a, I think it is not differentiating between these two, integer and long, in this implementation of C++. Other implementation or other compilers might have some different ranges for that, but it is, I think it is exactly the same. If you look over here and if you look over here, they are essentially the same. So I think it has, we are going to also verify it with the size of operator, so we're going to see that in a few minutes. So I think they are essentially the same, long and integer. But if we have double long, so we have, I think this thing is also same here. This thing is long and a simple unsigned integer. They're essentially the same thing over here. We have 8 f's over here, and we also have 8 f's over here. So we are talking like 32 bits, so it's going all the way from 0 to 4 billion. But here we have a long maximum and long minimum. So we are talking about the signed format, and whenever we are talking about the maximum only but not the minimum only, so obviously we are talking about the unsigned, because we have a u over here. So it has an unsigned long format. So let's count how many bits are there just by counting the hexadecimal. That's 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So we have 16 hexadecimal numbers. So each hexadecimal number is 4-bit, so that means that long is a long is 16 into 4 is 64, right? So 64 bit, and each and 1 byte is 8 bits. So that means that long variable or long object would be a 8 byte number. So it's a really large number, and it has an extremely large range going from, I mean, it's really difficult to figure out. Okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19. I mean, it's really long number. So we have going from 64 bits. So I think it's kind of a, let's try 64 bits. So 64 bits is 2 to the power, sorry here, 2 to the power 64. So that's what we have here, and if I divide it by 2, that's what we have over here. So that's the maximum possible negative number. Minus is actually this 8 over here. So, and the maximum positive number would be -1, and that's what we have here. I mean, it's a really large number. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18, maybe less. You can just go, I mean, it's like trillion billion possible range. So it's a really large number, but it's a whole number. So let's see some other, this is, I think, not used that often, because you can see that it is kind of an 8-bit type. So not that used often, but it is actually useful whenever you are dealing with some kind of a microcontroller which has limited memory, and there it becomes really important that whatever variables you are using, they should be of the right size, not too much, not too less. If you are having a smaller variable but you want to store some large value, it will have some kind of an overflow error. If you have a really a large variable but you're only going to store some really small value, so that would be a wastage of space. In computers, we have, even though we have like gigabytes of memory and we have like terabytes of hard disk space, but it's still do not use the variables which are too big for the values you are using, because that would be a wastage of space. I mean, if you are using like 1 or 2 variables, that's okay, but if you are writing really large programs and they are declaring values or arrays of values which are extremely large, but you are only storing some really small values, so that would be a really big wastage of space. So that program would not be that memory efficient. So we need to keep in mind that, let's say if I want to store values which go from 0 to 10, so I do not need more than a byte for that. Even then I can store like this thing in 4 bits actually. So a byte would also be a wasteful thing to do. Some programmers actually store 2 4-bit numbers in a single 1 byte number using some kind of a masking or something. Might be discussing that whenever we are discussing the bitwise operator, or you can look it up on internet. But the point is that now we have understood that computers can actually computers actually represent everything as number, and depending on what type of that that object is, either could be integer, unsigned integer, or long integer, that would be, or maybe unsigned or signed as well, that would determine what kind of values or what range of values could be fit inside that number. So that wraps up this lecture. In the next lecture, we are going to do the size of operator. We are going to demonstrate how to take the values as hexadecimal, and we were going to see that what the actual memory occupation or what the actual memory allocation each object has. If we are talking like integers, and we are also going to see what would happen if we exceed the range of the variable, such as if you're talking about the short variable and we try to store a very large number into it, and we will see that what kind of problems we will face, such as the overflow error or the kind of a cycle around error, because it will just cycle itself back to the initial value. So we are going to see that in the next lecture. In the end, the summary of this lecture is that we continued 2's complement representation, and we did few more examples, and we also saw the size limitations, and we visited the C limits and the limits header file, in which we saw in which we actually computed the range of variables depending on how many bytes that variable or variable type is actually occupying in the memory.